Okay, so I just wanted to walk you through the notes. We're going to go over these briefly in class, but I wanted you to have this to refer back to. So first off, we're going to be talking about measurements in physics and in any science class. And when we make measurements, we are going to be using SI units or metrics. And then going on from there, oops, okay. There are three resources here that you should be aware of. You don't need to look at these right now, but these three hyperlinks will take you one to here. And this is going to walk you through how to kind of set up your dimensional analysis, your factor label method on how to make conversions, whether we're talking about metric conversions or conversions between English and metric units. And so I am going to post another video that will walk you through how to do this, but please be aware that this resource is available to you. The other link will take you here, and it talks about units and talks about the difference between quantitative and qualitative measurements. And then it's going to walk you through metrics and our fundamental units and then derived units and things like that. And then the third resource on that page is the IB textbook. And this pages 1 through 7 will be very helpful for this week. But again, you don't need to go to those right now. Then there's one other resource on this next slide. And if you click on that, it will take you here. And you are going to need to refer to this slide when you are making your metric conversions, because you're going to need this right here. Okay. Okay, so on this slide, we're going to talk about when we make a measurement, we are going to record two things. And it's really important that you know that when you make a measurement, you record two things. One of those things is the quantity, the number, 9, 12. But the other thing that's really important is the unit. And so if you just say, oh, it was 9, well, 9 what? You really need to be specific, 9 centimeters, 9 liters, 9 grams. So we really need to know what you're talking about. So make sure when you make a measurement, you record both the quantity and the unit. The other thing with quantity, when we get into later on, we're going to talk about scalars and vectors. And vectors are things that have direction and magnitude. And a lot of times you're going to get confused with, well, what is the magnitude? It'll ask a question, will say, you know, report the magnitude of the force. Well, people get confused by that word magnitude. It's referring to the quantity. What is the number? Don't tell me about direction, just tell me the magnitude. What number was it? What quantity? Coming here. So then we have our fundamental units. Fundamental units are things that cannot be broken down any further. They are basic units that are measured directly, and from those units we get everything else. For example, if I measure time and I measure length, I can from that derive a unit of speed. So I can talk about meters per second, and that is going to come from these fundamental units. And so for right now, we're going to really focus on length, time, and mass. So first off, when we talk in physics, we're going to start off with these three, and we really need to get these down right away. So when we talk about length or distance, we're going to be using meters. When we talk about time, it's our second. And when we talk about mass, we're going to refer to the kilogram. So our standard unit of length is the meter. If you come down into the speaker notes over here, you'll see right here a link. And this link gives you a little bit of background on where the meter, how it was defined, and how it's been kind of changing throughout time and becoming more and more precise. You don't need to look at that. If you would like to look at that, feel free. It's there for you. But you just need to know that when we make measurements, we use meters. Length, measurements of length, we use meters. The next measurement we're going to use is time, and you're familiar with time already, and our unit is going to be seconds. Once again, if there's a link down here, if you're interested, feel free to go to this and kind of see how that unit of time has been measured using the cesium atom. But again, you do not have to do that unless you're interested. The next one is the unit of mass, not to be confused with weight. With mass, we're talking about the kilogram. And once again, there is a link down here if you're interested in seeing how that has changed over time. When we talk about mass, we will be using kilograms and grams. So then we get to the derived quantities. And so I touched upon it earlier that the derived quantities come from our fundamental measurements. And so if I'm talking about velocity, velocity is a measure of distance divided by time. And that's why our units are meters divided by seconds, or meters per second. Acceleration is a distance divided by time divided by time. So meters per second squared, or meters per second per second. Force, we're going to use a Newton, but a Newton can be broken down. Force comes from mass times acceleration. So a kilogram meter per second squared. And for energy, we're going to use joules, and joules are a Newton meter is the unit that we're going to use. Okay, so when we get to unit analysis, when we talk about the quantity versus the unit, so looking at things like displacement. Displacement is a fancy word for distance, but it's distance with direction. So if I were to walk from here, walk 4 meters, say, and then walk from here and walk up 3 meters, you can see that I've walked 7 meters. But that is not my displacement, because displacement is going to be like the shortest distance between 2 points. And so I walked from here to here. It was a roundabout way, but that's the way I went. So you should be able to see that this is a 3, 4, 5 triangle. If this is a right triangle right here, this is a 3, 4, 5. And so the distance I went from here to here is 5 meters. Okay, speed. When I come over here and I look at this speedometer, I can see it's a little past the 80. It looks to be about 82. And if I'm here in the United States, that's going to be registering as 82 miles per hour, mph. You'll see it as miles divided by hours, or you might see it as miles and then hours to the -1. So that they all read the same thing, miles per hour. If I'm talking about pressure, if I look at this pressure gauge and I see it, it's about 375 psi, pounds per square inch. I would write that as pounds divided by inches squared, or pounds inches to the -2. Taking that a little further, your units are really helpful in determining if you're doing things correctly. For instance, if I'm looking at acceleration, I know that acceleration is a change in velocity, delta v, divided by a change in time, delta t. And so my change in velocity is going to be meters per second, and my change in time is going to be seconds. So I have meters per second divided by seconds. So my answer needs to have the units meters per second squared, or meters per second per second. And so your units, if you're doing it right, are going to tell you if you did it right. For force, force is mass times acceleration. And so my units of force are going to be my mass, which is kilograms, times my acceleration, which is meters per second squared. So I'm going to have kilogram meters per second squared. Now that unit has a special name. It's named for Sir Isaac Newton. And so these are units of newtons. All right, so let's see how dimensional analysis is going to play a role in solving physics problems. So we're given this formula that distance is equal to velocity times time. And the problem is, suppose the velocity of a car is 36 miles per hour and it travels for 4 seconds. Show that the distance traveled in that time by the car is 64 meters. So we need to recognize here that here we have miles per hour. Our answer needs to be in meters, and here we're given seconds. So clearly we have some conversions we need to make. So the first thing I do is recognize that I have miles per hour and I have seconds. And my answer needs to be in meters. I'm given the formula that distance is velocity times time. So I need to know that my miles need to become meters. So I need to make that conversion. And I've got to be able to cancel out my seconds with my hours. So I have some conversion factors. I know that 1 hour is equal to 3,600 seconds because there are 60 minutes in an hour and 60 seconds in a minute. 60 times 60 is 3,600. I also know that 1 mile is 1,609 meters. Now that's not something you need to memorize. You'll be given that information. So when I set this up in my dimensional analysis, my factor label method, I have 36 miles per 1 hour, 36 miles divided by 1 hour. And I'm multiplying that by 4 seconds. because of my formula. Distance is velocity times time. So now I've got to try to make my conversions. So I'm going to take my equivalency here. My 1 hour is 3,600 seconds. And I need to figure out how I'm going to cancel out this hour. Well, if hours is on the bottom here, I need hours on the top to cancel out. So I write this as hours over seconds. 1 hour per 3,600 seconds. So my hours here are going to cancel out. Then I take my other equivalency, that 1 mile is 1,609 meters, and I'm going to write that in such a way that it'll cancel out my miles over here. Now, miles is on the top over here, so miles needs to be on the bottom over here in order to cancel out. So I have 1,609 meters per 1 mile, okay? And then my miles will cancel out. My hours are already canceled out with my seconds, and the only thing I have left is meters, and that is my answer. If I multiply 36 times 4 times 1,609, and then divide that by 3,600, I'll come up with 64 meters. The really cool thing about dimensional analysis is that you can use the units to make sure you're doing things correctly. So in this slide here, we have velocity is equal to distance divided by time, okay? And velocity is meters per second, meters divided by seconds. Well, distance is measured in meters. It's one of our fundamental units. Time is measured in seconds. It's another fundamental unit. So we have meters divided by seconds. So meters per second equals meters per second. So now I know that that formula is correct. So is this formula valid? We have distance is equal to acceleration times time. Well, distance is meters. Acceleration is meters per second squared, and time is seconds. So my seconds here will cancel out one of my seconds here, so I'll have meters per second. Well, meters per second is not equal to meters, so this is not a valid formula. So our next thing is orders of magnitude, and we're going to be using this when we talk about scale. So orders of magnitude is a fancy way of saying powers of 10. So if I look at my chart over here, if I talk about billions, I'm talking about 10 to the 9th. Well, the order of magnitude is that 9. If I'm talking about hundreds, that's 10 to the second. The order of magnitude is 2, okay? And if I were talking about the difference in the orders of magnitude, the difference between 10 to the second and 10 to the 9th, that would be the difference in that exponent. So the difference would be 7 orders of magnitude. The difference in the order of magnitude between the mass of the universe at 10 to the 50th kilograms and the mass of a quark at 10 to the negative 30th kilograms, I'd have 10 to the 50th divided by 10 to the negative 30th. And when I do that, I have 50 minus a negative 30. So that means 50 plus 30, which means I'd have a difference in order of magnitude of 80. Here's a list of some various orders of magnitude, looking at, again, the mass of the universe, the age of the universe, and you can see there are huge differences in orders of magnitude. All right, so here's another one. So given that the smallest length in the universe is a Planck length of 10 to the negative 35th meters, and the fastest speed is the speed of light at 3 times 10 to the 8th meters per second, show that the smallest time interval in the universe is about 10 to the negative 43 seconds, okay? So we're just going to focus on that order of magnitude, the 10 to the negative 35th and the 10 to the 8th. And so if I do time is equal to distance divided by velocity, then I'm going to have my 10 to the negative 35 divided by 10 to the 8th, and I'm going to have 35 minus 8 is going to give me 10 to the negative 43rd. So that is going to be my smallest measure of time, 10 to the negative 43rd seconds.